Welcome back. Let's continue on chapter 6, section 4. We did part 1. This is part 2 of that section. Last time we discussed the derivative of logarithmic function, the natural logarithmic function. Today we're going to talk about more general cases for both exponential and logarithmic function. So let's start with the general form of exponential function. Let's say b to the power x, where b is the base. It could be any number. One positive, b greater than 0 and b not equal to 1. These were the restrictions for the base. So how do we find the derivative? Naturally, there is an idea that we can always implement. So here is the idea. If we call f of x to be y and say y equals b to the power x, we can take a natural log from both sides of this equation and create ln y equals ln b to the power x. And if you remember, one of the properties of the exponential function is that you can, the logarithmic function is that you can drag down the exponent as a coefficient. So I can drag down this exponent x, write it down up front as a coefficient. So it would be x times ln b. Now, if we take a derivative of this, what do we think we get? So if we take a derivative with respect to x, what do we get is derivative of ln y would be 1 over y. This is what we learned. Multiply by chain rule derivative of y with respect to x. And on the right hand side, what we get is derivative of x ln b. Ln b, this is just a number. Log of b is a constant, ln of a constant would be another constant. So this would be something, for example, like 2.3. So you have x times 2.3. The derivative would be simply derivative of x, which is 1 times ln b. So what you get is simply 1 times ln b. Write it this way. Because ln b is a constant. So what we can do is find out what is dy over dx. So what would be dy over dx? It would be multiply both sides by a y. So we get y times ln b. And we can say, what was y originally? Originally, we let y to be equal to bx. So I can say, this can be equal to b to the power x ln b. And what do we found is the derivative of y with respect to x, which is b to the x ln b. So here, we found out the derivative of the function f. If f is chosen to be b to the power x, the derivative would be b to the power x, very similar to the e to the x, the derivative is the same, multiplied by the differences ln b will show. If b turns out to be e to the power x, then e to the power x derivative would be e to the power x times ln e. But ln e is simply 1. So we don't really need to write that. We write e to the x. It still shows that the derivative that we found, the general derivative that we found, it satisfies still the natural exponential e to the x. And the general case is if you have chain rule, if f of u is given b to the power u and we're looking for the derivative with respect to x, f prime of u would be b to the u ln u. This is just the derivative of the exponential part, multiplied by the chain rule u prime, or you can write it as du over dx. So this would be if we're implementing chain rule. If u is a function of x and we're taking the derivative with respect to variable x. Okay. Similarly, we can create derivative for general function of log. So if we have log x base b, how can we find the derivative? This one is kind of simpler because we know one property. We can rewrite, simplify the function f as log x base b. By the change of base property, we can write this as ln x divided by ln b. These two are the same by the log property. So now if I can ask you what is the derivative, this could be written as 1 over ln b times ln x. Again, This is a constant. ln b is a constant. There is no variable involved here. The only thing that we need to take the derivative if we're looking for f prime x, we should say this is a constant, so this stays the same. Multiply by the derivative of ln x, which is simply 1 over x. So we found out what the derivative of f of x is. And normally they write it this way. They write it as 1 divided by in order x times ln b. Just to make sure that x and ln b, you cannot put the x inside the ln b. Maybe use parentheses here. Similarly, if f is a general function, a function of u, and you want to take the derivative with respect to x, this is taking derivative with respect to x, then you can say derivative of log u base b would be 1 over u ln b multiplied by u prime or d of u with respect to d. Again, this is just a chain rule. This is chain rule implemented on the general log function. The derivatives are very similar. See, derivative of e to the x would have been e to the x. Now in this case, derivative of b to the x, maybe I should have that. Derivative of b to the x turns out to be b to the x multiplied by an extra term ln b. And derivative of log x base b, if it was ln x, derivative would have been 1 over x. But since there's a different base, there would be an ln b showing up. And extended, the chain rule is simply just this extra term multiplied du over dx. du over dx. This is the derivative of the inside function. The inside function could be the exponent or the input to the log. So let's do a couple of examples. Maybe I should mention this here. Yes, I wrote it to mention it as well. The integral of b to the x dx. Now we can answer this. If it was, let's go back up. If it was b to the x ln b, the integral would have been b to the x. But without the ln b, so what would be the integral? It would be 1 over ln b times b to the x plus some constancy. The general form of the log doesn't really need anything. If you have 1 over x ln b and you want to take the integral of that, you can always assume that this is a constant, so you can always write it outside. You can write it as 1 over ln b integral of 1 over x. And we already know this derivative, this integral. This would be 1 over ln b times ln x plus some constant. That's why we don't really require the integral of the log, general log. This, by the way, this could be written as ln x divided by ln b, which is the same as log x base b. And you notice that it doesn't really need you to use the general when you're taking the integral, because you can always break it up, take out the constant and use the ln function. This is just a simplification. If they ask you to combine the two log and write this 1, then you need to do this. Otherwise, it's totally fine to just leave it as ln. So let's calculate some of these derivatives. What is the derivative of 2 to the power sine x? If it was 2 to the x, what would we do? Let's say, so if I write it 2 to the u and ask you what is the derivative, you should say it is 2 to the u multiplied by ln2, ln of the base. This is so far, this is just the derivative of exponential. And by chain rule, you multiply the derivative of the inside, which is the u prime. So in this case, we get 2 to the sine x, that's still there. This is 2 to the u multiplied by ln of 2 multiplied by, now by chain rule, you should multiply the derivative of the exponent, sine x, the derivative, which you can write it as 2 to the sine x times ln2 multiplied by sine x derivative is cosine x. And here we have the derivative. There's no way to simplify this, so leave it as it is. And how about this one? 3 to the x squared times e to the tangent x. Still, again, all these properties that we learned from the derivative, they still, you should still implement those. So here we have product of two functions. You should use product rule. You should say, let me actually shift this up a bit. Sorry about that. Let me draw this. D over dx. Okay. But we still have to implement product rule. So we should say e to the x squared. By the way, e to the x squared is the exponent here. There is a difference. I'll show you the difference later, but maybe I should have used parentheses just to make sure there's no mistake. 3 to the x squared times e to the tangent x. If we're taking the derivative, we should say derivative of the first term multiply by the second plus 3 to the x squared multiply by e to the tangent x derivative. Maybe I already used bracket. Let me stick with the bracket. Okay. So now at this point, what is the derivative of 3 to the x squared? It would be 3 to the x squared multiply by ln 3 multiply by the exponent derivative 2x. Okay, let me write it just to make sure that everyone follows this step. This is the chain rule implemented into the first bracket. Multiply by e to the tangent x is still there. Plus 3 to the x squared multiply by e to the tangent derivative. It will be e to the tangent x. The derivative of e to the u was e to the u. ln of e doesn't really need, we don't need that. You don't need ln e because this is simply 1. So it would be e to the u times u prime times tangent x derivative. And finally, you can write everything 3 to the x squared multiply by ln 3 multiply by 2x. We use parentheses just to make sure that the ln 3 is separated from the 2. Multiply by e to the tangent x plus 3 to the x squared multiply by e to the tangent x multiply by the tangent x derivative is secant squared x. And here we have the derivative. It's still, again, you're implementing power rule, product rule, even though there is exponential function. So those quotient rules, power rules, everything's still there. And by the way, I wanted to mention this, that there is a difference between 3 to the x squared and 3 to the x squared. Make sure that you know the difference between these two. This one, the right one, this is what we have at the moment. And sorry, the left one, this is what we have. The right one, this is the same as 3 to the 2x because you can multiply the exponents. So make sure that if you're using this case, maybe it's better to use parentheses. Without the parentheses, this is what it means. With the parentheses, that means there's a power. You should multiply those powers. Okay. So let's calculate the derivative of this log function. By the way, I didn't write the base. So in this case, the base is simply 10. If you forget that, you may miss one term. So what would be the derivative? This input is the same as u. Log u derivative, case b, would be 1 over u ln b multiplied by u prime. This is the chain rule. So it would be 1 divided by x ln x, this is u, multiplied by, don't forget this term, ln 10, ln of the base. Now multiply by the inside derivative, x ln x derivative. And then this term outside is still there, x ln x times ln 10. Don't worry about simplification till the end if you want. Multiply by derivative of x ln x. You should implement product rule. X derivative times ln x plus x times ln x derivative. And finally, you can write that as 1 over x ln x times ln 10 multiply by derivative of x is 1, so 1 ln x plus x times derivative of ln x is 1 over. You can cancel out these two x's and you'll get ln x plus 1. That would be the simplest form of this derivative. Okay. So here, how about we calculate this derivative? Derivative of 3 to the power 2 to the power x. So this is a composition of two exponential functions. So what would be the derivative? Derivative of 3 to the power 2 to the power x would be 3 to the power 2 to the power x. This is the u term. 2 to the power x is the same as the u. Multiply by ln of the base, ln 3. Multiply by the exponent derivative, 2 to the power x derivative. So then we have 3 to the power 2 to the power x multiplied by ln 3 multiplied by 2 to the power x derivative is 2 to the power x multiplied by the derivative of the base ln 2. And here we have the derivative. It's not complicated as long as you stick with the same rules and make sure that you do not forget those ln of the bases. And here is an example that I've seen students struggle with when they see pi. They will freak out. It's no different than anything else. So here we have the derivative of d over dx of x to the power pi. So what is the derivative of x to the power? Let's ignore the pi at the moment. If they ask you the derivative of x to the 3, this should be simple. 3x squared. Subtract 1 from the exponent, drag down on the exponent, and subtract 1 from the exponent. The important thing is that you do not see this as exponential. You should see this as a polynomial. If you're dealing with x to the power pi, the derivative should follow the same thing because it's not the exponent that is the variable, it's the base is the variable. So therefore we have a polynomial type. The exponent in this case is constant. The constant turns out to be some number 3.14, whatever that number is. So you're still implementing the power rule, not the exponential rule. So what would be the derivative? The derivative would be pi. You drag down the exponent, subtract 1 from the exponent. That's it. There is no more to this. This is the derivative of x to the power pi. So let me color this. I'm going to use green for these terms and red for these ones. So let's deal with the red ones first. Plus the derivative of log x base pi. Again, derivative of log x base pi would be 1 over x ln pi. That's it. There is no complication. Plus derivative of log pi over base pi. So I'm doing these terms 1, 2, and 3 in order. The third derivative would be log pi base pi. What is the derivative of that? If you focus on this term, you notice that there is no variable involved. Everything is constant. By the way, I can change this to square root, cube root, whatever that is. Everything is constant. So the derivative would be simply 0. You don't need to implement the log derivative. That's a constant, so the derivative is 0. How about we look at the green ones, 1 and 2. Derivative of pi to the x, now that's an exponential because it's the exponent that's the variable, not the base. So the derivative would be using the exponential rule, pi to the power x. Again, think about it as 3 to the x. How would you take the derivative? You say 3 to the x multiplied by ln of 3. So pi to the x multiplied by ln pi. And how about the derivative of pi to the power pi? To the power pi, to the power pi, doesn't really matter. All these are constant. There is no variable x involved. So the derivative would be simply Okay, so make sure that you differentiate between polynomial and exponential function. And if you're dealing with constant, there is no need to implement power rule or exponential rule. Okay, so this is the derivatives. Integrals are simple. I'll do an integral at the end as well, but it's the easiest ones are the integral. Okay, find the derivative. The derivative for these specific functions, x to the power x, g to the power g, x to the power sine x, log x base 2 to the power tangent x. I'm going to do each one separately. But what do you see about these type of questions is that if you look at the f function, for example, both the base and the exponent are variable. So you have x to the power x, and taking the derivative is not that simple because you cannot implement the power rule. You cannot say this is x times x to the power x minus 1 because the exponent is not constant. Neither you can implement the power rule, the exponential rule, because the base is not a constant either. So what you need to do in these cases is stick to this idea of using the logarithmic form. So here, this section we're going to talk about is logarithmic. Is a trick that we use to calculate the derivative for the general exponential function. So we're going to do that as well. So let's find the f prime derivative. We want to find the f prime derivative first. So f prime x question mark. I'm going to use red. Okay. Again, let's replace f with y. What do we have? Is y equals x to the power x. Always when the base and the exponents are variables, normally you'll go with this idea. So the idea is you take a ln from both sides. Ln y would be equal ln x to the power x. So far we haven't taken the derivative. Why are we doing this? Is to get rid of both base and exponents to be variables. So in this case, the right hand side could be simplified. Properties of log is you can drag this x down as a coefficient. So what I can do is write it as x times ln x. Now, can I take a derivative here? I should be able to, because everything is in a form that I can take the derivative from. So I'll take a derivative here. And what would be the derivative? Derivative of left hand side, ln y, would be 1 over y. Sorry, let me write it here. 1 over y dy over dx. Derivative of right hand side, what is x derivative ln x? You should use product rule. It should be 1 times ln x by product rule plus x times derivative of ln x is 1 over x. You can simplify it a bit. You get 1 over y dy over dx equals ln x plus these two can cancel out and we get plus 1. Okay, so what are we looking for? We're looking for, again, this is what we called y. We're looking for dy over dx. That's the question. So solve for dy over dx. I can multiply both sides by y. You multiply both sides by y. And use parentheses. What do we get is dy over dx equals ln x plus 1 multiplied by y. Now what is y? Y is simply ln x plus 1. Because we're replacing y because at the end, the derivative should be independent from y. It should be a function of x only. And y was originally, we called y to be x to the power x. So x to the power x. So what did we find? Find that dy over dx equals ln x plus 1 x to the power x. And you notice that it's not following exponential or power power rule. It's kind of a combination of both. So we have ln x plus 1 multiplied by x to the power x. That is the derivative of this one. So that's it. There is nothing more to it. Here, If you look at the second example, gx equals x to the power sine x, you can implement the same idea. So here we have, let me write g of x here is x to the power sine x. I think I picked x to the power sine x. Yes. So what do we do? First step is you say y equals x to the power sine x. If you're looking for the derivative, then take an ln from both sides. So therefore ln y would equal ln x to the power sine x. You can simplify the right hand side. The ln y equals sine x times ln x. You can drag down the exponent. Now that everything is in terms of product, there is no exponential form, we can take the derivative. So I'm going to take the derivative of this and say, okay, what is the derivative? The derivative would be 1 over y equals, use product rule. Derivative of sine is cosine x multiplied by ln x plus sine x times the derivative of ln x, 1 over x. And on the left side, I forgot the dy over dx. Sorry about that. Again, you can solve for dy over dx. Multiply both sides by y. And use parentheses. These two can cancel out. You have dy over dx equals cosine x times ln x plus sine x divided by x, at 1 over x could be written divided by x times y. And we found out what dy over dx is. This is dy over dx equals to this. The only important thing is that sorry. I wanted to choose a different color here. Get rid of this y, because the function at the end should be a function of y. The result should be a function of x. So g prime x, the derivative, would be cosine x ln x plus sine x divided by x multiplied by y, but y is simply x to the power sine x. Y was x to the power sine. And that's it. That's the derivative. We can do the other example now. hx, which is log x base 2 to the power tangent x. I picked the complicated ones because the easier one, I didn't want you guys to say, okay, he did the easy ones, left us with the complicated ones. So here log x base 2 to the power tangent x. You can take the derivative, not here, because both the base and the exponent are variables. If the base, for example, if this was log 5 base 2, now you should use exponential because this is a constant. Think about it, if it was 3 to the power tangent, what would you do? Do exactly the same thing, just replace 3 at the end with log 5 base 2. Okay, in this case, if it's variable, then you have to use this technique. Okay, so there are shortcuts for it, but I recommend using this technique to avoid making mistakes. So y would be equal to log x base 2 to the power tangent x. Then take an ln from both sides. Ln y equals, I've done this already, so I'm going to skip this step. Drag down the exponent as well. ln of log x base 2. Okay. So I drag down the exponent by taking the ln from both sides. Take the derivative. 1 over y, dy over dx. Derivative of right hand side, derivative of tangent times ln. Be secant squared x multiplied by ln log x base 2 plus tangent x. Here's important. How do you take the derivative of this term? This inside first, you call it du. You think about it as a combination of two logs. This is an input to the other. The derivative of ln u would be 1 over u, which is 1 over log x base 2, multiplied by u prime by chain rule. So what is the u prime? It would be log x base 2 derivative. So what is log x base 2 derivative? It would be, we learned that today, 1 over x ln 2. This is the derivative of log x base 2. So now we found the derivative. We can find out what is dy over dx. dy over dx equals, multiply both sides by y again. It will be secant squared x times ln log x base 2 plus tangent x times all those terms. I can put it in the denominator, log x base 2 x ln 2. And since we multiply both sides by y, there should be a y here. So at the end, you replace y with this thing. So finally, h prime x equals secant squared x times ln log x base 2. You need to practice this a lot just to make sure that you get the idea. After a while, this technique is very useful for taking derivative in a complicated case as well. Sometimes you're dealing with a fraction and it's complicated. You can use this technique of taking log. Multiply by y was at the end log x base 2 to the power tangent x. Okay, this is this technique of taking logarithmic from functions that have both base and the exponent as variable. And here, sometimes they'll ask you these questions as well. Let me write this with right. Given the function f of x is cx plus ln cosine x, if the derivative is given at a certain point, can you find out what is c? So you use this information given to figure out what is that constant c that is given here. We're trying to figure out what is this constant c. So what you need to find out is first the derivative, then replace pi over 4 for it, set it equal to 6, and that means you have to have one variable at the end, and that variable is c. You'll figure out what is that variable. So first find the derivative. What is f prime x? C is a constant, so the derivative of cx is simply c times 1, which is c, plus derivative of ln x, ln cosine x, is 1 over cosine x, multiply by derivative of the inside, derivative of cosine, negative sine x. Chain rule. And so we can write this as c minus sine divided by cosine is tangent x. And what do we know? We know that the derivative at pi over 4 equals 6. That means if you replace pi over 4, f prime of pi over 4, which equals c minus tangent of pi over 4, must equal 6. Must equal 6. So now we have an equation. C minus pi over, tangent pi over 4 equals 6. What is tangent pi over 4? Tangent pi over 4 is simply 1. So you have c minus 1 equals 6. Therefore, c must be equal to 7. It's not complicated as long as you get the question and you use the given information. In this case, this is the given information. And we're looking for this coefficient. If it was the second derivative, you need to find another derivative. And I told you I'll do an example of the integral. So here's an example of the integral. If it was simply, if they ask you to calculate the integral of pi to the x dx, by the way. Since we know the derivative of pi to the x would give you pi to the x times ln pi, this means you need to have an ln pi somewhere. 1 over ln pi, pi to the x. This is the integral plus some constants. This is the integral of some constant to the power x. So now, what we can do is generate examples for using substitution. So here in this case, you need substitution because the exponent doesn't look that simple. It's not simply x. So what we can do is we can say let u equal x squared. Then what would be the derivative? du over dx would be 2x dx, sorry, 2x. And I went ahead a bit. Du divided by 2x would be simply equal to dx. You can update the boundaries if you want, 0 to 1. I'm going to do that just to make sure we still remember that. So what is u? If x is given, let me write it here. If x is given 0, if x is given 1. I'm using this to update the boundaries. If x is 0, u must be 0 because x squared is equal to u. X equals to 1, u must be equal to 1 as well. 1 squared equals to u. In this case, the boundaries didn't really change. So this would be from 0 to 1, x times pi to the power u times, instead of dx, we have du divided by 2x. The x's will cancel out, and we have integral 0 to 1 pi to the u, multiplied by du over 2. du over 2 can be written as 1/2 du. You can always get rid of the constants by putting it up front. Just do not write 2 times that. It's 1/2 times this. Keep the 1/2. What is the integral of pi to the u? I just mentioned it. It would be 1 over ln pi. Sorry, ln pi. Such a bad handwriting. 1 over ln pi times pi to the power u. Evaluate it from 0 to 1. You don't need c since we're evaluating the boundaries. If you replace 1, what we get is 1/2 ln pi multiply by. If you replace 1, we get pi to the power 1. If you replace 0, you get pi to the power 0. What is pi to the power 0? It's simply 1. So this is simply 1. Pi to the power 1, simply pi. So what we have is 1 over 2 ln pi times pi minus 1. That's it. This is the integral. This is the integral of x times pi to the power x squared. You can create other examples, but they're very similar to this. That's why I only picked this one. Taking the derivative is much harder than finding the integral, because the integral you can always use substitution, and the substitution requires taking the derivative properly. Okay, this is it for this section, part 2. I'm gonna stop at this point. We'll continue this chapter next time.